engineering a sustainable future with social responsibility is my vision for the George R. Brown School of Engineering here at Rice, and sustainable energy and chemical production are at the heart of this vision. Indeed, we just yesterday announced the launch of reInvents, which is the Rice Engineering Initiative for Energy Transition and Sustainability, and to coordinate our efforts in this space and to amplify our efforts so that the school's impact in the space of energy and renewable energy is much, much larger than the sum of research taking place in individual labs. As we are all aware, the world faces two major challenges, so many challenges, but two of them are hundreds of millions of people lack stable access to energy across the globe, and most of the current energy production used to power our world and produce materials we use every day produces greenhouse gas emissions that endanger the environment around us. Today's lecture highlights 3 Rice engineering faculty that aim to disrupt the current methods of energy and chemical production through innovative engineering solutions. This includes the development of new renewable energy sources, materials to reduce energy needs for chemical production, and the shift of oil and gas from fuels to high-volume materials. And now, it is my great pleasure to introduce our first speaker. Our first speaker is Aditya Mohiti, who is an associate professor of chemical and biomolecular engineering and the inaugural director of our reInvents initiative that we launched yesterday. Aditya received his PhD in electrical engineering from the University of Louisville in 2007 and did his postdoctoral work at Rice University here. He joined the George R. Brown School of Engineering and the Chemical and Biomolecular Engineering Department at Rice as an associate professor in 2018. As I mentioned, he's the inaugural director of our initiative for energy transition. Aditya is interested in understanding and controlling photophysical processes occurring at the interfaces created with layered 2D materials, organic and inorganic materials for thin film light, to energy conversion technologies such as photovoltaics, photocatalysis, etc. He's also interested in the application of correlated interface sensitive techniques such as photocurrent time resolved PL and so on. I do hope his talk will be much less technical than what I just mentioned now. So with that, it's my pleasure to introduce our first speaker, Professor Aditya Mohiti.
Good evening, everyone, and thank you, Luay, for this wonderful introduction. It's absolutely fantastic to be here, and thank you for Lisa for nominating me to present this really prestigious lecture. As the title of my talk suggests, today I'm going to tell you about really how do we harvest the power of the sun, right? Through making photovoltaic devices which are really low cost, these are disruptive, but then also trying to take this energy and figure out ways to store it. And so what I'm going to be talking about is basically asking 3 questions. What is the role of solar energy for decarbonization? And I think everyone's heard that solar is really ubiquitous and that's going to play a really important role. What is the current status? Where do we really stand? Because everyone talks about using renewables for powering everything. And so the question is, do we really have enough? Are we really scaling so that we will have enough renewable resources to power the planet, to power our processes? Okay? And then finally, as I said, to store solar photons for on-demand energy. One of the challenges, as I will talk about, is the intermittency of solar, right? That's the biggest challenge. The sun doesn't, it's quite predictable. It doesn't shine 24/7. In fact, it shines about 5 or 6 hours a day, at peak voltage. So those are the topics I'm going to cover. So let's get started. Let's look at this picture, which I'm sure each of you have probably seen before. I'm showing you the global CO2 emissions, and this is plotted as gigatons of CO2 emitted per year. Okay? And then, of course, what it also shows is the different scenarios that we face for the climate change. And what we are trying to achieve is the 1.5 degree, or prevent the 1.5 degree rise in temperature. And so you can see that based on this, right, by the mid-century, we really need to scale this, we really need to bring this down quite dramatically. And in fact, even by 2030, you can see we have to halve this. So we are at about, so if you look at where do these really emissions come from? Here's sort of the breakdown of this, right? You look at that, electricity and transportation, right? That constitutes a huge amount of CO2 emissions, right? That's more than 50% of what's being emitted today. Okay? There's other things like food, industry, decarbonizing the industry. It's a big one, right? That's something that, being in Houston, we have to kind of think about. Nature. And so this total comes out to be about 60 gigatons of CO2 emitted per year. And so the good thing about this, this distribution is that electrification transport constitutes 57% of the CO2, right? And 65% of the world population lives where we can use renewable energy to overcome this. In fact, replace fossil fuels or complement fossil fuels for getting this type of energy. Another curve that people often think about is the carbon intensity. And I think being in the energy capital of the world, people think about energy intensity, which is basically the grams of CO2 that you would have to emit per kilowatt hour of energy that is produced. And so you can plot that curve just like that. And actually, if you look at this curve, you'll see that it's quite depressing because by 2050, we need to generate 90% of the energy that we use today using sources that are different than fossil energy. Also, this means that in the next 10 years, right, we will have to change all the systems which generate energy or store energy using renewables and other means of doing this, right? And I think that we have not really appreciated what this really means, right? And so this is an incredible challenge. And so the way to think about this is that the first thing we need to think about before even thinking about what science or technology will do is we have to think of scales. How do we do it? What technologies scale? And how can we do it fast? And so I would like to, and this is something that John Doerr has given us. There's a prescription for doing this, speed and scale. And I would encourage you all to kind of go to that website. There's tremendous amount of information available which you can access. And so since we are talking about scales, this is what we have, right? These are renewable sources. And again, you may have seen this picture. And this is what we have. We have wind, we have ocean, tide, biomass, hydroelectric, geothermal, and solar. And so what's very clear from this picture that you have tremendous amount of, you basically have a nuclear reactor in the sky that is really abundant, ubiquitous, which would meet all the demands that we need. And so if you look at that, that's about 36,000 terawatts of power, which is incident on Earth, on land, right? And so if by about 2050, what we need to power our civilization is about 35 terawatts. And so this makes sense that if you can actually harvest this energy, then we should be able to address a large part of this energy. We should be able to produce this for cleaning up our planet. And so I spoke about scales. And so the first plot that you see is that typically if you look at the energy industries, energy doesn't scale. Electronics scale. If you look at Moore's law, right? Moore's law scales number of transistors that you can pack. That has been scaling, right? But the only technology that's really scaled is photovoltaics. You can see this plot. What I'm plotting on the left is the installed capacity, which is in yellow. And on the right, I'm plotting the levelized cost of energy. And you can see that there has been at least a 100x decrease in the cost of this over the last several decades. This is quite unusual. And if you compare that, if you take the price of an oil barrel, right, fossil fuels, in the 70s or in 80s, you will see that that's remained quite flat. In fact, it has probably only changed by a factor of 2 or so. And so that's quite impressive. So you have solar energy, which can scale like this, okay? So that makes sense. And so where are we today? Well, here's where we are. This is till about 2020 or 2023. And so we need to get to about 800 gigawatts of power, right? And in order to do that, we will have to increase the installed capacity of solar by about 3x times faster than we are doing it today, okay? And so while people talk about renewables powering all kinds of processes, this is not a given, right? This is not as straightforward as you think it is, because there are challenges associated with it. Okay. So the current landscape of solar, let's get into this. Photovoltaic technology today is the world's largest optoelectronic industry, right? Greater than 160 billion, more than LEDs, more than flat panel displays. And this is going to reach about 300 billion by 2030. And this is dominated by silicon. Okay? In fact, silicon efficiency, silicon's really the king of photovoltaic devices. If you look at the efficiency of a silicon solar cell, that's at about 25%. That's the power that you get out of silicon. And if you look at the module efficiency, when you scale this up, you get about 18%. And so this cost now is at about 25 to 40 cents per peak watt hour, right? So this is the DC power that is produced. And what I'm showing you here is a picture, which is this Bhadla solar plant, which is the largest solar installation that's going to happen, that's happening in India. This is going to have a capacity of 2.5 gigawatts. So that's the current status. But as I mentioned, that one of the biggest challenges for solar is that its intermittency and the capacity factor, right? The sun doesn't shine. In fact, it's very predictable that the sun doesn't shine. And so you get a curve which looks something like that. Insolation here means how much of light is really, what is the exposure, what is the libido of light that is incident on your solar panel. And you can see that that peaks at noon, right? That makes sense. And so if you look at the capacity factor, which is defined as the average power generated in 24 hours, divided by the peak power generated in noon, you'll see that that comes around 10 to 25%. And that's quite low, right? And so consequence of this was shown by Sivaram and co-workers, where they showed that this leads to sort of deflation as we get to more and more market penetration. On one hand, we want to expand solar panels and install capacity, but on the other hand, you're going to get this deflation in their price because of more penetration, because of this capacity factor. And so that means very simple things, that we need to reduce the cost even more, right? So let's look at where we are at today. So we've, of course, done really, really well. This is, again, the same type of plot. What I'm plotting is the levelized cost of electricity as a function of years. And you can see that it's coming down. It's done remarkably well. And this came from the manufacturing of silicon, which was in Asia and China. And that's at about 20 or 25 cents a watt or kilowatt hour. Okay? And what I would like to also show you is this equation which gives you that cost, which is the levelized cost of electricity. And you will see that there are these costs associated with this. There's a module cost. There is a balance of system cost. There is an efficiency which is there. And so if you look at a panel today, right, the material cost is just 25% of that panel. Right? All the other cost is associated with balance of systems, which means all the other costs which are required for that panel to produce power. This would mean transmission, inverters, switches, converting your energy from DC to AC, all of that. Okay? But, however, if you look at this equation, one thing that lies is this efficiency. If we can improve the efficiency of this process, this lies in the denominator. And so by decreasing the cost, it may not matter so much. But if you increase the efficiency by twice of where we are at, then that could make a huge difference in the levelized cost of electricity. And so how do we really do that? Well, we don't really have the technology to do it today. We need to think of new materials, new physics. And so that's what I'm going to be talking about. What is that? Right? And here's another curve. And again, the point I want to really make here is that this is the silicon curve, right? Which this is the reduction in price. And you can see that this type of a curve comes from an experience, it's an experience curve, which means you're not going to get the same type of drop in cost from silicon again. All right, so getting into this, so let's look at, this is an eye chart, and I apologize. There's lots of information on this. But the only thing that you need to look at is this, this black line. That's the silicon efficiency. That's at 25%. And so what happened about a decade back is that there is a new kid on the block, which is known as these solution process halide perovskites. It's a new class of materials which has surpassed the efficiency of silicon. In fact, if you combine this material with some other materials, like for example with silicon or itself, you can get to efficiencies which are very, very high, which is actually shown on the top right here. We are already at 32%. And so what are these halide perovskites? Well, it turns out these perovskites is a mineral. This existed since about the 18th century. And the nice thing about this is that you can take this material, you can put this in solutions, and then you can coat that on any surface that you want. You can do this, you can spray coat this, you can spin coat this, you can paint it on walls, and it gives you a remarkably efficient photovoltaic device. Another nice thing about this material is that you can tune the colors, right? You can get rainbow colors, and so we know from the physics that if I can then combine different colors of these perovskites, then I can go beyond. I can make these multi-junction cells which have efficiencies which can go above 40%. And so that's now possible to do with materials like this. And also the nice thing is that everything can be done at around 100 degrees C. They can be recycled completely at 100 degrees C. And you need about 1,000x less than what you're using today, which is silicon. However, there is a problem. Okay? If you look at a curve that is produced from a photovoltaic device, that from a perovskite solar cell, you'll see that it starts off at a nice number, about 20%. But then after 400 or 500 hours, you'll see that it has lost some efficiency. And that is not good enough, because what we are trying to make is a technology for photovoltaic devices or solar cells that can last for 20 years on a roof. Okay? And so that was not good enough. And what my lab has been working on is to address this issue of stability. And so I'm very happy to share that we have some really exciting breakthroughs where we can now combine a few different perovskites and create a photovoltaic device which has 25% efficiency, but then get stability, which is the curve on the right. I'm showing you the power conversion efficiency as a function of time. This is tested in the lab under one sun illumination, under operating conditions, and you can see that we barely get any degradation. And so this is a huge breakthrough in the field, and we think that this is really the pathway for commercializing the solution-based technology, which has really been the dream of many researchers since decades. And these are some publications that we've had over about 5 or 7 years. The nice thing is also that we have now several patents, and First Solar, which works on thin film PV, is interested in, expressed interest in licensing this technology. So in addition to this, some other things you can, as I mentioned, that we can make tandem cells now. We can take solutions, we can spin coat on top of each other, we can combine that with silicon, and we are looking at efficiencies of about now over 30% very consistently. We can also think about other applications like photovoltaics for water, for desalination, flexible, for Internet of Things. And so this is a remarkable technology that can be used just beyond utility scale PV to distributed to even using for these type of applications. Okay? All right, so as I said, solar is great, but we also need storage. And so one way to store solar energy is to convert and make fuels out of this, liquid fuels. And I think you will hear these really exciting talks going forward by Naomi and Matteo, who will talk a little bit more about this. But one such way to do is to be able to generate hydrogen. Everybody wants hydrogen these days, and so if you can split water using this really low-cost photovoltaic device and get high efficiencies, then this would make a lot of sense. And so these are some things that we have been doing. And what we've done is we have taken these devices and created an integrated photoreactor where we can take these low-cost solar cells, interface them with water, with the catalysts, And we are able to achieve efficiencies over 24%. This is solar to hydrogen conversion. This is number of photons coming in to the number of moles of hydrogen produced. This is a world record. And as you can see on the right, I'm actually showing you a curve which says that the predicted efficiency of this is only 22%. And so the question is, how do we get to 24? Well, it turns out that in addition to the electric power that is produced, we can also harvest the waste heat in that solar cell, and that gives us a boost in efficiency and gets us to about 24%. And so that's been very exciting, and the next steps for us is to be able to really stabilize the system and to be able to scale it up. Finally, in my last slide, I want to show you where we are. So I'm plotting the solar to hydrogen efficiency as a function of stability, and you can see that we are right on this top right corner. That's the record that we have. And another nice thing about this is that if you look at if you do the techno-economic analysis for this type of a technology, we are at about $1 a kilogram. And this is quite exciting because that's really what the DOE target is. It's 1 kilogram of H2 at $1 in about a decade. And so by improving the scalability, improving the stability of the system, we feel that there's lots of exciting things that could be really possible. Okay? So with that, I just want to thank again the School of Engineering, Dean Luay, Lisa for this tremendous opportunity. I want to thank all the collaborators, Jackie even, who's here and has been a great collaborator here visiting us from France. My group, who's been just amazing, who's really stuck with me of thinking of a lot of these problems, thinking of out-of-box ideas, and all the collaborators, Mike Wong, Chris Conrad, for working on the PEC project. We're very happy to take questions. Okay.
Thank you so much, Aditya. We'll take questions at the end. And now it is my great pleasure to introduce our second speaker for the series, which is Professor Naomi Hallis. Naomi Hallis is the Stanley C. Moore Professor of Electrical and Computer Engineering, with appointments in Department of Chemistry, Physics and Astronomy, Bioengineering, and Material Science and Nanoengineering. She is the founding director of the lab for nanophotonics at Rice University and director of the Smalley Carl Institute, focused on advancing nanoscale science. Furthermore, effective just last month, Naomi was named University Professor, which is the highest and the most prestigious title that we saw than a professor. Naomi received her PhD from Bryn Mawr College and then served as a postdoctoral researcher at AT&T Bell Labs before joining the Rice faculty in 1990. Naomi's research interests lie in the area of optics and photonics and the design and fabrication of optically responsive nanostructures, nanophotonics, and plasmonics. I will not list much of Naomi's awards and recognitions because that will take about 15 minutes, but I will just say that Naomi is a member of the National Academy of Engineering, the National Academy of Sciences, and the American Academy of Arts and Sciences. We are very, very proud to have Naomi among our faculty and our second speaker.
Normally I wouldn't quote a politician, but this politician is quoting scientists, so I think that that's a legitimate quote. And it's very interesting to see what he said a couple of years ago now, that he was told by scientists 50% of the reductions we have to make to get to net zero are going to come from technologies we do not yet have. So that really, really puts the onus on basic discovery science and exploration science, not just in developing. We heard a great talk about developing and pushing some already understood technologies like photovoltaics forward, but then we also need to be discovering entirely new things to do. So let's talk about a problem that you might not think about when it comes to energy. This is actually a photograph of the Dow plant in Freeport, Texas. And I visited there once. They told me they had 4 reactors, and one of their reactors could power Chicago. And that's very emblematic of the fact that when we look at energy use across industry, we find that the chemical industry is actually the big bad boy. Right? They have a tremendous, tremendous energy consumption. So if we really want to solve problems like decarbonization, it would be very wise for us to ask the question, can we make chemistry more sustainable? Okay, so what is the issue with chemistry? The issue is, of course, well, as you know from modern materials, many of them are made using oil and gas as feedstock, right? Using petroleum hydrocarbons, as feedstock, but also they're used by creating heat and temperature and pressure, right? That's sort of the standard way you run a chemical reaction. We all learned that, right? You heat up the chemical reaction. So it's the fossil fuels that we're using to drive the chemical reactions, in addition to, which is much, much greater than the feedstock that is used, that really causes all the issues with a huge amount of CO2 production and the issues for the chemistry limits. So what about, how could we envision something else? Rather than using heat, can we use light? And if we use light, so electrically driven light, then we could actually electrify chemical production, and we could drastically reduce the carbon footprint. So the way we do this is by using these beautiful nanoparticles that sort of come from, so we're starting from my lab. So we start with gold. Here's an example of gold nanoparticles discovered in ancient, beautiful artifacts understood by Michael Faraday in the dawn of classical electromagnetism. So what a metal nanoparticle does is it captures light. It acts like a little optical frequency antenna. So it captures light from far away from itself, and it focuses light around itself. As it does that, it generates hot electrons, and those hot electrons can move to the surface. If there's a molecule on the surface, then they can do chemistry. And so we know that the hot electrons generated from metal nanoparticles, what we call plasmonic nanoparticles, can drive chemistry. And the name of this is photocatalysis because it's driven by light, but it's more than that. It's driven by the hot electrons that we generate in metal nanoparticles. So here's a little cartoon that illustrates a very, very simple reaction. What we're going to do is we're going to break apart a hydrogen molecule. Hydrogen is isotropic to helium. It takes very, very high energy. It's a very high barrier to dissociate a hydrogen molecule. But it turns out we can do this on a gold nanoparticle surface just by shining light, transferring an electron to the H2 molecule, making it H2 minus, and put it actually in an excited state, and then dissociating this essentially at room temperature. We're not raising the temperature at all, and we're lowering the barrier by more than a factor of 2. So this is a way to get around this bottleneck of using so much thermal energy. So why is this better than heating? So let's think about all chemistry is really just the making and breaking of chemical bonds, and those are electrons. Right? So if you put in heat, you put in heat to all of the aspects of the system. You cause vibrations, right? So you have many, many degrees of freedom. You're exciting all of them when you apply heat. Heat is very, very non-specific. So you're wasting a lot of energy in vibrations when really all you want to do is put in the energy directly into the electron that will do the work to dissociate the molecule. So if we only excite the electrons, we will have much, much more efficient chemistries. And we'll be able to do them at low temperatures, and we'll be able to also do them using light. And so one of the biggest revolutions recently is the fact that now light is very cheap. People have thought about using light-driven chemical reactions since the 1970s, but they use lasers, and lasers give you very, very expensive photons. But it turns out that with the revolution of solid-state lighting, we can actually think about using renewable energy to generate solar electricity, to generate electricity, and then to drive LEDs of very, very high efficiencies of the exact right wavelengths that we would need to drive those nanoparticles then to engage in the chemical reaction of interest. And so this makes it practical. This makes it inexpensive. And so in order to do this, we had an idea. And in fact, I'll say, so first of all, my colleague Peter Nordlander had the idea. This was an idea that came from theory, not experiment. So he's a theorist in his office, and he realized that we can take this optical antenna and then we can dress it with other little islands that are reactive. So the problem with gold is not very many things stick to gold. So if I want to do a chemical reaction, I have to put in something that will grab that reactant like a handle, and will do the chemistry and then let it go. And so how do we do this? We can combine the optical antenna functionality of a metal nanoparticle. It can be gold, can be silver, in this case aluminum or copper, and then puts very small islands on the outside, which are where the reaction happens. So we call them antenna reactors. Thought this was a good idea. We tried it in the laboratory. It worked really, really well. And so we patented it. And then after we published the paper, these two guys sent us email. These two guys, Trevor and Suma, two young, hungry, courageous Baker Hughes engineers. They sent us both emails. They'd like to commercialize our concept, our patent. And I deleted the email. Peter did not delete the email. Peter met with them. And about 10 minutes into the meeting, he called me up and he said, "You've got to meet these guys. These are the real deal." And this started us on the really exciting journey to watch this idea, this discovery, leave our laboratory and then move into commercial activity, as I'll describe in a few minutes. So what are some reactions that we did? So one of the reactions that's important is ammonia decomposition. Well, what in the world does that have to do with the energy transition? It turns out ammonia is an almost ideal hydrogen storage medium. Right? It is, of course, it's carbon-free. If you could have a way to release the hydrogen easily, if it wasn't done at high temperature, then you could basically ship ammonia all over the place. You can ship it in pipelines, large ships transported across the ocean. And so all farmers have it. You could put it in their tractors if they wanted. And so so the question is, could we do ammonia decomposition with light instead of heat? And that's actually what I'm showing you here. So you can look at the little cartoon, because the cartoon's very cute. It shows a copper nanoparticle with little ruthenium sites. But then the thing you want to look at is the plot right below it. That shows us turning light on, turning light off, turning light on, turning light off. This is something chemists can't do. You turn the light on, you make hydrogen, you turn it off, it stops. Okay? This is the fundamental game-changing difference between thermal chemistry and chemistry by light. It really is hydrogen on demand. And you can also see, if you look carefully at some of the other plots, that this is much, much more efficient than what we see with what we would have with thermocatalysis. Reaction number 2 is a reaction that's done in industry all over the place, and that is taking methane. It's called methane reforming. So that take methane and combine this with either water, CO2, and you make hydrogen. So 90% of the hydrogen, that is produced industrially is produced this way. It's an endothermic reaction, so it occurs at very, very high temperatures. So if we could lower the temperature of this, or maybe even do this without increasing the temperature, then we could really be able to, again, have hydrogen in a very useful way. And so, so in fact, the answer is yes, we actually were able to do hydrogen specifically, no back reactions, no side reactions, and so on, without an external heat source. So light only. The light is, as you shine light, you do have a small residual photothermal effect, but that's not actually what's driving the reaction. And the energy efficiency is a record energy efficiency of 35%. And so they started a company. I told you about Trevor and Suman just a minute ago. They started a company named Syzygy. They just actually hired their 100th employee about a month ago. And so their vision was taking what we call the fairy dust, the nanoparticles that we make, and then building around this a technology of solid-state lighting-based chemical reactors instead of thermal reactors in order to drive this. And so if you think about it, now all of a sudden I don't need high temperature. I don't need high temperature materials. So low temperature materials are much cheaper. I can do this with aluminum instead of high alloy steel, for example, and I can also run this with with renewable energy instead of fossil fuels. And also, as I sort of alluded to, these catalysts keep themselves remarkably, they essentially regenerate. They keep themselves very, very clean. And so this is a picture of one of the reactors that they designed. As soon as they build one reactor and then another reactor and another reactor, larger and larger as they scale up, they save the reactor and they put it in their own museum so they can keep a history of how this has scaled up. But this is a reactor designed by photonics engineers. It's not designed by chemical engineers. There's chemical engineers working on this, but really it's a light harvesting problem that then drives the chemistry. So how does the reactor work?
Syzygy's photocatalyst is a nanoparticle system that is made up of 2 parts. It is composed of a larger, light-harvesting plasmonic nanoparticle, which is covered with much smaller catalyst nanoparticles. Photons are made using high-efficiency LEDs, and these photons interact with the plasmonic nanoparticle to produce plasmons, which in turn energize the catalyst nanoparticles. This interaction causes the catalyst to generate high-energy electrons that are able to make or break chemical bonds. Inside of Syzygy's reactor, this basic process of using photons to perform chemical reactions happens more than 1 trillion times per second. Ultimately, this is how our chemical reactors work.
So they have scaled up from basically laboratory reactor off on the left to their reactor, actually one step larger than what I showed you, by a factor of about a 500,000. And they're now moving towards, they are actually at their final stage reactor that they call Rigel. Rigel is a blue star in the the constellation Orion. And because they use blue light, they thought this would be a great, use a giant blue star as the name. So Rigel produces hundreds of kilograms a day, and this is now in field trials. And the idea is once Rigel is ready for delivery, then you can, of course, produce tons of hydrogen. You're making basically reactor banks. And so you have all sorts of possibilities for producing very large amounts of hydrogen, also small amounts of hydrogen, all electrically. And so of course, as you go up in scale, and then of course electricity is trending down, you can see where water splitting is, and you can see where, so they're just beyond the 200 kilograms a day. They're moving now towards the last point. And so we watched them grow. Just since 2018, we watched them grow from a small group of about 5 initial employees. Now, as I mentioned, they have hired their 100th employee, and they now have a big facility on Sam Houston Parkway, so you can drive past and you can say, you know what this is. And most recently, we did a very exciting experiment with them, and rather than telling you about it, I'll let you watch the video, if I can play the video. This paper boiled down to an amazing discovery. We were looking at a very important reaction, ammonia decomposition. This is very important for the hydrogen economy. And we started by working with our antenna reactor nanoparticles. So these are particles that are activated by light, but they do chemistry. And they can convert a catalyst, a well-known thermal catalyst where people use heat. They can convert the thermal catalyst to a light-based catalyst.
Well, catalysis is the foundation of chemical industry, and that's one of the most energy-consuming parts of all society. The catalyst makes the chemical transformations easier.
We started the experiment by using a copper antenna and a ruthenium reactor. The ruthenium is where the actual chemistry happens. And then my student had a really clever idea, a kind of crazy idea. He said, instead of ruthenium, which of course is very, very expensive, why don't we try iron?
So my whole work is built on this ideology that we want to not only do a reaction that is beneficial, but also find a catalyst that is much more abundant, much more cheap, much more sustainable than what we had before.
So that's the first innovation we do here. We show that catalysis can be done by these very cheap and abundant materials, sustainable materials. Perhaps even more important is that we can do this with light. Okay, so we don't have to heat up a reactor. The heating up of a reactor is a very slow process. It requires very high-grade materials, high pressures, high temperature. When we do it with lights, we can basically do it in a very small, we could do it in a plastic container, obviously we don't do that, but we go to very low temperatures and very low pressures. So it's a very sustainable, it's a very little investment in that kind of equipment. Perhaps even more important when it comes to hydrogen, which is the focus of this science paper, is that we can do it on the fly.
Because you're using less energy, this could also enable decentralized plants, and this decentralized plant actually can produce hydrogen which depends on the need of the customer. In terms of like a near-term goal, we are trying to deploy this technology in different parts of the world to produce green hydrogen. For example, Scientia Plasmonic joined an agreement with Lotte Chemical and Sumitomo Corporation to deliver fully electrified ammonia cracking plant to help South Korea to decarbonize.
And this is being developed in Scientia Plasmonics, which is a company that Peter and I co-founded. So this type of technology is being used to drive chemistry based on our antenna reactor nanoparticles, our antenna reactor complexes. And so we show in this work
that LED-based chemistry is actually doable, and it's doable at scales that can actually contribute to industrial scale chemistry and industrially important reactions.
When we burn hydrogen, we generate water. You can't think of anything more sustainable than that.
So we're on quite an adventure with antenna reactors, and really we think that this is just a complete revolution in chemistry. This is really going to change the way chemists think about doing chemistry going forward. So thank you very much. Happy to answer questions.
Thank you so much, Naomi. And our last speaker is Matteo Pasquali, who is the A.G. Hartog Professor of Chemical and Biomolecular Engineering, Chemistry, Material Science, and Nanoengineering at Rice, where he also serves as Director of the Carbon Hub, which is an ambitious new initiative that aims at using hydrocarbons as feedstock to produce clean hydrogen energy and high-value carbon products that can be used in place of conventional materials with large carbon footprints. After receiving his PhD from University of Minnesota, he joined Rice University in 2000 to start a lab on soft materials, which evolved into Key Center for Scalable Manufacturing and Application of Carbon Nanotubes and graphene materials with enhanced mechanical, electrical, and thermal properties. He is also a fellow of the American Physical Society. Matteo.
Thanks, Luay. All right, we talked about sun, we talked about hydrogen, now we got to talk about carbon. I'm going to tell you about the carbon shot. Climate solutions. So Aditi and Naomi talked about some of these. There's a lot of things that are being discussed. For example, we talk about industrial decarbonization. The chemical industry is one part. Metals are much bigger. The CO2 emissions and energy consumption coming from metal making are about 5 times bigger than the chemical industry. We need hydrogen, and hydrogen is a solution for all of these problems. For example, you can decarbonize steel, or you can decarbonize ammonia production if you have hydrogen coming from solar. But then you end up putting more and more pressure on solar and wind. Right, so we need the renewables. And as Aditi was talking about, with the current way we make solar cells, pretty quickly we end up against some barriers on how to have enough resources to make them. And so what I'm going at, it's this is like trying to kill the hydra. You push on one side, you kill a head, and another one comes up. For example, I'll give you another example, a couple of examples. We want to electrify. Right? We want to electrify everything. If we're going to electrify everything, we're going to need a lot of copper and aluminum. These are nasty materials. You know, they require a lot of mining. They require a lot of resources to be converted from ore, which are aluminum oxide and copper sulfides, to the actual metals. And so, is there a way to address many of these problems at once? And slaying the hydra, right? And then that's what a carbon shot is about, is finding a way to use carbon that actually addresses many of these problems at the same time. First of all, carbon leaves a rise. Carbon was kind of a moribund effort when I was in grade school and high school. It's kind of boring. And then Rick Smalley and Bob Curl discovered a new form of carbon, the fullerenes, and this spawned a renaissance for carbon. And you know, here I have just some of the older people who are at Rice working on carbon, and some of the younger people up with Seiichi Matsuda on the top left, the recruiting class of chemistry. And it's also an area where we had multiple institutes. We have multiple institutes and a number of successful startups. And it's also one of the places where we've been able to train graduate students and postdocs who are now faculty at MIT, Georgia Tech, Penn, and Stanford, and other of great universities. So it's our legacy and our future. So what I want to talk about today is something, think about carbon differently. Like carbon has gotten this bad name because we call carbon dioxide carbon. But carbon is an element, it's not carbon dioxide. So think about a future where we could actually strip carbon from hydrocarbons. And these hydrocarbons can come from various sources. It could be fossil, or it could be biogas that comes out of a landfill, for example. And we use the hydrogen for clean energy, and we use the carbon to displace other materials. So we could split them, and then we could use some scalable processing and efficiently take this carbon and turn them into products, into usable shapes, fibers, fabrics, tapes, that are endowed with properties like electrical conductivity, thermal conductivity, strength, that overlap with the other materials we want to displace and have mechanical integrity. I'm not talking about something that we need to invent. I actually got samples here. This is something that can be made already, and we can have show and tell at the end if we have time. And they're safe to touch, so even if there is a reception, we can still touch. And then we need to take this material and scale as fast as we can and put it into applications. Build wires, cables, parts of components of cars and trucks, and maybe even things that we cannot do now, like integrate with clothing. I encourage you to touch these materials to see how nice it will be. And if we do it well enough, this could be the material where we build our infrastructure, like bridges, houses. So how does this come about? Well, when I came to RISE, I thought that making materials out of carbon nanotubes was lunacy. They could make just a little bit of a spec in 2000. They had no idea how to take this stuff and assemble it. And it was so interesting that in 2004, we actually were a team led by Rick Smalley, in which I was a member. We made the first fibers of carbon nanotubes. The properties were terrible, and we got it published in Science. That's how excited it was that we could even make a fiber. But then, by working hard and doing science, and for example, following a paper that Boris Jakobson had written in 2000, and he said, you need to make the nanotubes longer. And we had to learn how to measure these and how to make them longer. And by making the nanotubes longer, the properties got better and better. So every 3 years, we double the properties. And every 3 years, we double the strength and the electrical conductivity. That was it's been a great collaboration with June Conn on understanding how to increase the conductivity. And so when you do that, and also we learn how to make materials on a larger scale, spun out a company called Dexmat that makes some of the larger samples. And eventually we got to the point a couple of years ago where the properties are good enough. So these are property maps. What you want to be on the top left, right? It's you want to have a high conductivity, high strength, high thermal conductivity, high modulus. And when you're on the top right of those maps, you can start displacing the other materials. The other materials are, the blue are metals, the yellow are carbon fibers, and the green are polymers. So the material now is good enough that it can displace these other materials. And it has a lot of other attributes. It's flexible, it's chemically resistant like all carbon. Carbon is earth abundant, so it's recyclable, safe. So why is it that we don't have it everywhere? Well, this, again, I'll explain actually something that Aditya only alluded to. He talked about the levelized cost, right? So this is a plot from the Sunshot when Ramesh, about 15 years ago, was looking at how can you get electrical energy to be on power with coal, nuclear, and natural gas. So you have to push down this levelized cost. And what needs to happen now is we need to push down some sort of levelized cost so you could buy a wire made out of these carbon materials. It would cost about the same for the functionality it makes as a wire of copper, or as a wire of aluminum, or as a bar of steel. And of course, each one of these materials is occupying different areas in our production systems, and also they're graded. So it's a lot more complicated as a problem. But also we need to do, and the way we need to do this is to follow the example of solar. So Aditya showed you the right part of the yellow curve. Solar starts actually in the 60s as technology to power satellites. And it had to come down almost 5 orders of magnitude in cost before it became cost parity for civilian use, and now it is actually cheaper than most other technologies. And it turns out that the cost reduction curve for carbon material has gone down very dramatically. But it's not there yet, so we need to push. So that blue dot is the shot that we need to take. We need to push down the cost of these materials into tens of dollars a kilo, and at that point we can compete with other materials. And one question is, where is it going to happen? This is what happened with solar, right? All the early work was done in the US, and then we lost focus, and now we buy solar panels from China, and we're trying to reshore production. Well, this is actually what happened also with carbon nanotube materials. It's initially was in the US, and then it moved to China, and then even to Russia. So but there's still lots of work to do. And the way you can think about this, you have to work in university labs, and you have to work in companies to scale up. University labs can produce these major innovation, like Naomi said, the light reactor, this idea of using a catalyst where you can use light instead of heat to drive the reaction. And then you have to go through scale-up phases where you reduce the cost by making things larger and more efficient. And the two have to interact because you want to keep introducing innovation as scale-up happens. So what are the challenges we're facing? Well, the first one is the first step. How does it work? Well, Naomi hasn't made us a photocatalyst yet, so we had to use heat, unfortunately, but I haven't given up. And so we bring in hydrocarbons and a catalyst, which is iron in this case. We provide heat, and we decompose the catalyst precursor and make the catalyst on the fly in the reactor and activate the composition of the hydrocarbons. And if we do it right, we make the right type of carbon materials. And there's a lot of questions, for example, here, these are simulations by Boris Jakobson that are showing that you really can make two types of carbons at the same time. The gray is the carbon we want, this is a carbon nanotube, and the red is a carbon, in this case, that we don't want, which is what we call amorphous carbon. So how do we tune the catalyst and the reaction conditions so that we promote the catalyst, the reaction we want? And how does this work in a complicated reactor, which has also heat and mass transfer and other phenomena? Scalable processing, this is what my group has done more. Now, initially, with funding from the Air Force, the way we got properties is the way people built Ferraris or Lamborghinis. You don't care about cost. When you're doing that, you just care about properties. And so it turned out when I had these ideas, we're going to use this stuff for large-scale materials, and we look at this process, and like, well, this is not going to work. We're using acetone, which is a very high CO2 footprint material, as part of the process. We use very low concentration of carbon nanotubes in our spinning. We're spinning slowly. And so we had to redesign the whole process, and we had to understand the fundamental fluid mechanics and transport phenomena of what happens when you extrude a liquid solution of carbon nanotubes and sulfonic acid, which is their solvent, into water and manage that process of removing the solvent. And so, and you have to keep the same properties, because if you make a bad material, then nobody's going to want it, no matter how cheap it is. On the top right, we have the old process. It's actually that roll is moving. You can't quite see it, but it is moving. And that's how fast we can go now. And we completely removed all organics out of the system, and we can increase the concentration of carbon nanotubes by a factor of 10. So the cost down, it was massive. It's about a factor of 300 between intensification of the spinning and the speed up. Again, a lot of basic science had to be done this, including things like inventing how do we image a vitrified acid. How do we take this solution, put it in an electron microscope, and image what it looks like so we know whether we have a solution or not, and how do we image when we have a liquid crystal. And so then there is also challenges in design and manufacturing. For example, if you think about, if you look at a plastic fork and a metal fork, they look different because the properties are different. Plastics are more flexible, so the plastic fork actually is a little bit thicker than the metal fork. And the way you make it is different. And so we're learning how to do these things too, and we're also learning out how do we understand the levelized cost. So we did a study with Doug Nathanson, Matt Foster, June Kono, Jeff Wemeyer, myself, a spin-off from Prismian Group, and we asked the question, if we make transmission lines out of this, how does it work? And it turns out that even though this material is a little bit less conductive than aluminum, there's about a factor of 2 in specific conductivity, lower, because it's a lot stronger and it's lighter, it would be possible to space out the towers that hold the power lines much further away. And that's where most of the cost it is to lay a new power line. It's the towers. It's a lot of, and also that's where most of the CO2 footprint is. It's a lot of steel and a lot of cement. And so in this case, by looking at actually a real application, we saw that by looking at the whole cost and also the whole impact of an installation, we could go, we could already do better with this material compared to incumbent conductors if we make it cheap enough. But in terms of properties, it's already there. So there's a lot of people who got involved in this arise. Of course, some of this is historical. We were already working on carbon, but now we're looking at not just to make carbon better, but to make carbon less expensive and make carbon that has no CO2 footprint. So there's about 45 faculty involved, and we have about $5 million a year of external funding that goes to these groups. And so we started the Carbon Hub to organize this. So why do we do this? There's a saying is you miss all the shot you don't take. And so if you don't know that there is a shot here, we're not going to take it, right? And so what the Institute is doing, the Carbon Hub or the initiative, whatever you want to call it, is also saying this exists. This is a way to use carbon that is more valuable than the ways we have now. Okay, we shouldn't just do carbon capture and the technology we already know. As Naomi said, that there's a lot of technology that has to be invented and deployed. There's an aspect which is a consortium because it has research funding, and we're also trying to foster and accelerate the creation of companies so we can have also an acceleration. We're funded primarily by Shell and Saudi Aramco, but we also have companies that are in a sort of like virtual supply chains. For example, Prismian Group, it's the biggest manufacturer of wires and cables in the world. And the reason why they want to work with us is because they want to stop buying aluminum and copper. That's their CO2 footprint. They buy aluminum and copper. They're the biggest buyer of copper in the world, and their executives right now are being assessed a penalty for indirect Scope 3 emissions of their products. Mitsubishi is part of this. Huntsman is actually already scaling up a process for making carbon nanotubes in this way. The next plant is being built in San Antonio. And so let me close with something. When we look at problems for climate, we can't only look at the U.S. We got to look globally. These are the CO2 emissions that come from steel. Okay, it's about 5 times bigger than the global CO2 emissions from chemicals. And so Bill Gates always says, what's your plan for steel when you talk about climate change? And our plan for steel, replace it, make steel obsolete, use carbon. So will you join us? Thanks.